Okay, so let me start my presentation. Also, it's a virtual conference, but welcome to Okinawa at 27 degree today. Today, I'd like to talk about our FPGA acceleration toolkit named OpenFC. As you know, HLS technology significantly improved productivity in FPGA design. It gives great efficiency in algorithm implementation, verification, and tuning. However, we still need to bridge between software and HLS designed accelerator modules. This part is usually called BSP or hardware shell and provided from the board vendors in several cases. The problem is when we need some customization on the shell or the shell is not provided by the vendor. Of course, the vendors are working hard on enterprise class accelerator cards such as Alveo or PAC. They are programmable through OpenCL based tools, but designing BSP or shell is almost impossible for end users because the very detailed specification is not open. So this kind of commercial tools are very good for data centers, but not good for custom FPGA cards or any other applications outside the data centers. So our goal is to provide an open acceleration toolkit for everyone and every purpose in this vendor-dependent way for both Intel and Xilinx FPGAs. The toolkit covers not only PCI Express based cards but also on FPGA SoCs with ARM processors. It enables seamless singular and multi-FPGA environments with vendors' HLS tools. So this figure shows typical hardware shell or BSP, including PCI Express, serial link interfaces, and DDR controllers. And also there is important room for acceleration logic. This is similar to the shells provided as part of commercial tools, but the commercial ones are not user modifiable, but OpenFC provides free open implementation, so it's portable across various FPGA cards. Here is the outline of my talk today. First, I'll talk about the OpenFC architecture, basic components such as the router, DMA controller, and processing elements in especially single FPGA implementation. Then it's about multi-FPGA extension with high-speed serial links, and I show some examples with performance evaluation. Here is the organization of our single FPGA shell with PCI Express DMA controller, the router, and partial reconfiguration controller. There is a router on the center to connect the DMA controller and processing elements or PEs. Users can design their own acceleration logic PEs. Then the PE bit stream is loaded through the partial reconfiguration controller PE through the PCI Express or XIDMA. There may be more processing elements such as DDR memory controller or high-speed serial link controller, any kind of control or status registers. It's up to the user's design. So the router is the core component of OpenFC. It provides common interface to all other components, including DMA, transceivers, and PEs. The interface is full duplex, 64-bit at 250 MHz. Of course, higher frequency is possible in recent, faster FPGAs for more throughput of the router. Also, the number of router ports is configurable on logic synthesis, so we can use in any scale. The router to accelerator interface is a very simple pipe-like streaming interface. Consists of data signal, valid signal, and back pressure signal. Any PE have at least one interface to router. So one interface consists of both incoming port and outgoing port. But it can have more number of interface ports for more bandwidth or more flexibility, depending on the flexibility or complexity of the program. So here is an example of with a router and PE. The data streams are basically source routed with the routing header. The routing header is generated and added by the host program. For this example, the first word of the routing header is, first word of routing header is the 2. So data stream goes to the port 2 of the router. There is a processing elements. Then the output of PE will go to port number 3 according to the routing header. It's a PCI Express interface to the host. The streaming communication between the host and accelerator is quite simple, as in this figure. First, the host program sets the host buffer with a header of PE number and payload length. Yeah, this one. Then invoke DMA transfer to FPGA. FPGA will receive the length header with its payload. Then acceleration pipeline starts. Then finally the host receive buffer will be filled by the result in blue. Because the router has OpenFC's original interface, so we need DMA abstraction or adapter modules for DMA controllers. OpenFC supports commercial ZBus DMA or refer DMA from UCSD and also XDMA from Xilinx on PCI Express. It also supports Xilinx Xi4 scatter-gather DMA on Zinc SoC environments. And because each DMA has its own DMA API, so OpenFC provides a lightweight API library to communicate with all supported DMAX. The API consists of device open and close, buffer allocation and routing, then DMA transmission and reception. There are also simple asynchronous I/O functions to handle simultaneous multiple stream I/Os. So here is an example using host-C API. So here is 2 streams transmitted toward FPGA and 1 returning stream from FPGA. The DMA transmissions to FPGA runs simultaneously with asynchronous API call. buffer send async. And here is the example on the processing elements in HLS on the other hand. The example is about the simple integer vector addition in C++ for Vivado HLS. Stream interface ports are described in using HLS stream class. And the main pipeline is simply written by for loop. In Intel HLS, we can use IHC stream in or IHC stream out class instead of HLS stream class. They are just same to this example. And this is about the multi-FPGA extension of OpenFC. OpenFC supports serial transceivers as implemented as a special processing elements that provides a transparent FPGA to FPGA or router to router channel. The transceivers are controlled by Aurora cores from Xilinx or its OpenFC clone called Kyokko. With Kyokko, Intel FPGAs are also supported, and both Intel and Xilinx FPGAs can communicate each other. So here is our demo system in action with two nodes with CPU and FPGA, and FPGA only nodes. The serial link is not an optical link, but CAPI links at just about 8 Gbps. And here is the result of stream benchmark. So So these green and light blue and pink lines are just with PCI Express, and other lines with circles are results from the remote FPGA beyond the serial link. So this figure shows that the use of remote FPGA is just about 90% of their peak bandwidth. For more realistic performance benchmark, two-dimensional diffusion equation solver had implemented in C++ with Vivado HLS. It's a typical two-dimensional stencil computation as this figure, calculating heat conduction or things alike. The result should be like this animation here. So, like other two-dimensional stencil implementation, the PE has stencil buffer that linearly hold all neighbor cell values. The line buffers are shift registers or block-run-based FIFOs, and pipeline consists of 7 floating point units. The PE can be cascaded to calculate multiple time steps at once. This enables smaller delta T for better precision of results, and also results in more gigaflops. And also the P's can be cascaded across multiple FPGAs through the serial links. And here is the performance results with 8 PEs to 64 PEs. The result showed almost linear speed up with reasonable efficiency Efficiency means the ratio of theoretical and observed performance in gigaflops. So with two FPGAs, the efficiency drops by 2 or 3%, but no more drops with more number of FPGA, so it's just working well, I think. Another example here is our radar system as the example of embedded application located in Niigata University on the roof. The system consists of Xilinx Ultrascale FPGA and DA/AD converters and amplifiers, and of course the antenna arrays. The control system or communication between ARM and FPGA is based on OpenFC, and the implementation was significantly simplified. To control status registers and DSP filter banks are between HDL but just connected to the OpenFC router. So I think it's good to use this toolkit. OpenFC in embedded system is also very good. And here is the size of router with different configuration of port number. 60 port router is still fits in 10% of Kintex Ultrascale 040, so it's very small. The latency is fixed to 5 clock cycles without any collision. And this result is about the serial link, Aurora, and our implementation, Kyokko. Kyokko core has just a similar user logic interface with Aurora, but it's smaller and latency is lower. It's just smaller even with OpenFC port adapter. So using Kyokko is currently a very good solution for multiple FPGA system. And here is a list of supported FPGA cards. There are many similar FPGA cards, so yeah, porting to a new card is not very difficult if you see the source code or ask me to port. The source code is available through our website and code repository. Some of the code is still work in progress, but if you send me request, I can provide some latest source codes. Also, Kyokko, the serial link IP, and Z5 driver is available from their repositories. So here is a summary of my presentation. OpenFC provides portable single and multiple FPGA hardware shell with simple host API. It provides basic facilities such as PCI Express, serial links, and parcel reconfiguration features. So users can concentrate their acceleration design both in embedded and HPC applications. Moreover, because OpenFC is very portable, so users can easily migrate to newer FPGAs. Yeah, thank you for attention.